Hello students, my name is Uttam Khoth from SIT COE Yadrao. From last lecture we are discussing about instrumental methods of chemical analysis. In last lecture we have seen some of the advantages and limitations of both the methods, nothing but the instrumental methods and non-instrumental methods. After that we have seen one technique, one of the method, nothing but the pH metry, how we can determine the pH with the help of glass electrode, with the help of pH meter, and what are their applications in the industry and in the case of domestic purpose. For today's lecture we are going to see second method, second technique, that is spectrometry. So what do you mean by spectrometry? It is a branch of science concerned with the investigation and measurement of spectra produced when matter interacts with the electromagnetic radiations. That means when electromagnetic light is falls on some kind of matter, some kind of solutions, what type of interaction takes place in between the matter and electromagnetic light, that can be get plotted as a response in the form of spectra, nothing but the spectrometry. In this method we are going to see some important terms from spectrometry and two laws which are very much important in case of spectrometry, nothing but the Beer's-Lambert's law and Lambert's law. And after that we have to see the instrumental part of the spectrophotometer, how it works and what is the applications of these, we have to see later on. Okay, before going to see the important terms, here I want to explain this one. As we know that sodium lamp or the halogen lamp gives white light with number of wavelengths, nothing but the polychromatic light falls on the collimator. Collimator inlines the all the lights from the source, okay, and falls on the some kind of prism and grating, nothing but the monochromator. Prism gives the light which is having rainbow color with different colors, actually different colors, and that light is falls on the slit. Slit allows only single wavelength light pass from it. Means that the light which is get emitted from prism having number of colors, number of number of wavelength, okay, but it when that light is passed from the slit gives only single wavelength light, nothing but the monochromatic light is get passed from the slit, falls on the matter. Here we can see solution is there, or we can say matter is there. When the monochromatic light falls on the some kind of matter, what kind of interaction takes place in between the light and the matter? Okay, we can say some part of light is get absorbed, some part of light is get transmitted, and some part of light is get reflected from the, we can say, container. Some part of light is get reflected. Means that three types of phenomenon are takes place when light is passed from the falls on the some kind of matter. Some part of light is get absorbed, some part of light is get transmitted, and some part of light is get reflected. Okay, that part is required for further discussion here. So we have to see here important terms. Number one terms which are very much important, that is transmittance. So how we can define the transmittance? Denoted by T. It is a ratio of intensity of transmitted light IT to the intensity of incident light I0 is known as a transmittance. Okay, mathematically we can say T is equal to IT upon I0 is nothing but the transmittance. So the first term. Okay, second term, absorbance or optical density. This term is very much important in case of the spectrophotometer. Okay, absorbance denoted by A or optical density denoted by sign D. It is the logarithm of reciprocal of transmittance is known as a absorbance or optical density. We can write A is equal to log of to the base E 1 upon T, or log of to the base E I0 upon IT, because it is the reciprocal of transmittance, where IT is equal to intensity of transmitted light and I0 is equal to intensity of incident light. Third term is the opacity. Opacity is nothing but the reciprocal of transmittance is known as a opacity. We can write opacity likewise 1 upon T is equal to I0 upon IT. Simple. Number fourth term, that is the absorption coefficient. Sign for that one is alpha. It is alpha. It can be defined as a reciprocal of the thickness required to reduce the light to 1/10 of its original intensity is known as a absorption coefficient. Is the reciprocal of the thickness required to reduce the light to 1/10 of its original intensity is called as a absorption coefficient. Number fifth term is the molar extinction coefficient. Sign for that one is the epsilon. It can be defined as it is the absorbance means A when the solution has thickness 1 centimeter and concentration of the solution is 1 mole per liter, means that molar extinction coefficient is the absorbance when solution has thickness 1 centimeter thickness 1 centimeter and concentration of the solution is 1 mole per liter. Then we can write is the A is equal to epsilon. Okay, these are the 5 terms: transmittance T, absorbance A, opacity, absorption coefficient alpha, and molar extinction coefficient. Next one. So we have to see here laws of spectrometry. As I said, one law is the Lambert's law, second is the Beer-Lambert's law, or we can say Bayes' law. Lambert's law especially is for solid matter, and Bayer's law, or we can say Beer-Lambert's law, is for solutions, okay, for we can say liquids. Okay, the first law, the statement for Lambert's law is when a beam of monochromatic light is passed through the homogeneous solution of absorbing medium, the rate of decrease of intensity of incident radiation with the thickness of medium is directly proportional to the intensity of incident radiation. Okay, mathematically we can write rate, that is rate of decrease of intensity of incident radiation, nothing but the minus di by dt, okay, proportional to the intensity of incident radiation I. Okay, we can write mathematically like this. Therefore minus di by dt is equal to ki, where k is the constant called coefficient of absorption. Okay, we can write here also alpha, also absorption coefficient. Minus di by dt is the rate of decrease of intensity of incident radiation with thickness T, and I is the intensity of incident radiation. We can derive this equation for further equation. minus di by dt proportional to I, we can get this equation. Okay, by rearranging that equation, likewise di by I we can get minus k dt. Okay, by applying the integration between the limits from I0 to IT and thickness T0 to T is equal to 0 to T is equal to T. Okay, so here we are applying the integration with the limits, okay, for the intensity and for the thickness here. Thickness is here and intensity is here. Okay, we can get the equation like this. By solving this we can get the equation like this. Log of to the base e it upon I0 minus kt. Okay, we can further solve like this. It is equal to I0 is equal to e minus kt. We can get it is equal to I0 minus I0 into e raised to minus kt. This is the equation for Lambert's law. Further, equation 3 gives it. By changing the log to the base 10 from e to base 10 for equation 3, we get it is equal to I0 log to the base 10 minus kt divided by 2.303. Here 1 upon 2.303 gives 0.4343 only. Because of that we can put here it is equal to I0 10 raised to minus 4343 kt. For k is equal to 2.303, we can put alpha here. It is equal to I0 into 10 raised to epsilon t. Now we can determine the intensity of absorbed light here. Absorbed light, as we know that absorbed light, as per the earlier discussion, we can get the intensity of incident light is equal to intensity of absorbed light plus intensity of transmitted light plus intensity of reflected light. But fraction of very small fraction of light is get reflected, which is very negligible. Because of that we can write I0 is equal to IA plus IT only. We can write intensity of IA is equal to I0 minus IT. Put the value of IT here obtained from the Lambert's law. IA is equal to I0 minus I0 into e raised to minus kt. We can get the equation for intensity of absorbed light from Lambert's law. So here it is, second law, that is the Beer's-Lambert's law. Okay, statement is similar to that one, but difference is that we are discussing about Beer's law, that means deals with the liquids, deals with the solution, means that we have to consider the concentration of solution. But for the Lambert's law we are dealing with the only solid matter. Okay, there is no matter of concentration. But in case of the Beer's law we are discussing here with the case of solution, means that we have to consider the concentration of the solution. When a beam of monochromatic light is passed through a homogeneous solution of absorbing medium, then the rate of decrease of intensity of incident light with the thickness of medium is directly proportional to the intensity of incident light as well as concentration of the solution. Similar to the Lambert's law, we have to write the equation here mathematically. Minus di by dt is the rate of decrease of intensity of incident light, okay, proportional to the intensity of incident light and concentration of the solution. Okay, further we can derive this one similar to Lambert's law. Okay, we can get the equation like this. It is equal to I0 into e raised to minus k dash ct. Here k dash is the molar absorption coefficient. Okay, here we can get the equation like this: IT is equal to I0 minus, sorry, I0 into e raised to minus k dash ct by applying the integration to the equation like this. Okay, further again, now by changing the base from e to 10 for equation 2, it is equal to I0 10 raised to minus k dash ct divided by 2.303. Okay, we can put value for k dash upon 2.303 as 0.4343 k dash. Okay, into the equation we can get, okay, as a epsilon it is equal to I0 10 raised to minus epsilon ct. Okay, now we are having equation, we can rearrange that equation: log to the base e it upon I0 is equal to epsilon ct log of to the base e to I0 upon it epsilon ct, because by rearranging the minus sign is vanishes. Therefore, as we know that I0 log of to the base e I0 upon it is nothing but the epsilon, sorry, absorbance. Absorbance is equal to epsilon ct, where A is the absorbance. C, when C is equal to 1 molar, okay, concentration is 1 molar, thickness is 1 centimeter, then we can write A is equal to epsilon. Absorbance is equal to extinction coefficient. Since for given system epsilon and thickness is constant, we can write absorbance is depends upon directly with the concentration. Thus, absorbance is directly proportional to the concentration of absorbing solution. Okay, this is the part of the Beer's-Lambert's law. So we have to discuss next part about the instrumentation part of single beam spectrophotometer. These are some diagrams. We can say single beam spectrophotometer or colorimeter, which is get used in the laboratories, which includes this much part. This is the, we can say, instrumentation part inside in the that single beam spectrophotometer, having this much parts in the instrument. Okay, the light source, that may be tungsten, halogen lamp, the collimator to collect the light, monochromator, that may be prism or grating, along with the filter. Prism or grating split white light into the color of rainbow with several wavelengths, and filter to select one color with specific wavelength. After that, slit is there, nothing but the wavelength selector to select the specific color wavelength, nothing but the monochromatic light. And after that, here it is a one cuvette container for the sample. We can take the sample in the cuvette. To hold the sample, we have to use cuvette. Cuvette may be rectangular or circular. After that, one detector is there to convert that photons, or we can say light, into electrical signal, electrons. After that, whatever the electrical signal is get passed to the amplifier. Amplifier amplifies that light, amplifies the electrical signal and gives to the meter. Meter shows the we can say reading, or we can say it can show the response. Okay, that is the, we can say, instrumentation part, construction part of the single beam spectrophotometer. Okay, here we can see the mechanism of the single beam spectrophotometer like this. Source gives the polychromatic light, which is get passed from number of mirrors, okay, by reflection. Pass to the prism. Prism gives the monochromatic light. Again pass from the sample. Sample gives the light which is get emitted from the sample falls on the detector. Detector detects that one and pass to the amplifier. Amplifies that signal and we can get the response as a spectra. We have discussed this one, the part of the we can say spectrophotometer. Source of light. The source of light should be emit radiations in the range of 400 to 800 nanometer. Therefore, tungsten lamp or deuterium lamp is used as a source of light. Monochromator is prism, cells or cuvettes, which uh, which are used for to hold the sample. Okay, which is, the solution should be homogeneous. Cuvette should be cylindrical or rectangular with accurate dimensions, made up by quartz and pyrex glass. Detector, that may be photovoltaic cell or photomultiplier tube, used as a detector. Okay, photovoltaic cell with amplifier and galvanometer is used to measure the intensity of transmitted light. Working we have seen. In this case, light which is get passed from the emitted from the source, pass to the mirror M1, again to the mirror M2. Same mechanism takes place. We can get the signal, and the signal which is get obtained on the meter as in the form of spectra. And this is the actually we can say working of single beam spectrophotometer, and that single beam spectrophotometer is used to measure the absorbance or transmittance of the materials or we can the solutions. Single beam spectrophotometer is used to find out concentration of unknown solutions. Okay, how that single beam spectrophotometer determine the concentration of unknown solutions, because we know that absorbance is proportional to the concentration of solutions. So we can write A1 upon A2 is equal to C1 upon C2 here. Okay, if absorbance of standard known solutions is A1, absorbance of unknown solutions is A2 are measured, then values of concentration of the standard solution is C1. Okay, and from these whole values the concentration of unknown solution C2 can be calculated from this equation. C2 is equal to C1 into A2 divided by A1. So we are getting the plot like this. Okay, from the plot actually, from the graph actually we are getting the value of concentration. We have to plot the graph absorbance versus concentration of various standard solutions, means that we have to measure, we have to take the absorbance values of known solutions with different concentrations. Okay, and that is get plotted on the plots graph. Okay, we can get the graph here, and we can determine the concentration of unknown solutions by knowing the absorbance of that one. Okay, we can get the concentration of unknown solution like this. This is the applications of single beam spectrophotometer. Next part we will see in the next lecture. Thank you.